Hello, ninth grade extended students. Today we are going to talk about mappings in space and in the plane. The first thing I'd like to talk about is rigid movement. If I have a copy of A and it changes neither in size nor shape as it moves from A to B. So as I look at this triangle, PRQ, the copy moves here to here. Since it didn't change in size and shape, this is referred to as a rigid movement. There are other types of movement as I'm mapping points in the plane, and these do involve mappings where my shape does change size. So one example is where I take triangle C here, this is triangle C, and it moves to triangle D over here. So I have a set of points all being mapped to this new set of points. You notice that C seems to have the same shape as D, but they are no longer the same size. So this would not be referred to as a rigid movement. Movement may not be well behaved. In this particular case, all these points are mapped someplace else, but you'll notice that they start as a triangle, but they end as something way different than that. So in the figure on the right, a copy of E is moving to F and becoming twisted and stretched as it does. Movements of points. The motion of the figures is made up of motions of individual points. There are infinitely many points along these segments in these triangles, and every single point is moving. You'll also notice that P is moving to P prime. We call that prime to indicate that I started off at P and it moved there. R moves to R prime, Q moves to Q prime, and there's lots of unlabeled points in both of those triangles. The motion can be described as an assignment of points. P is assigned to P prime, and Q is assigned to Q prime, R is assigned to R prime. In fact, to each point of triangle A is assigned a point of triangle B. So every single point in this triangle is assigned somewhere. So in exercise 116 in EMF, we want to explain the apparent motion in the second figure above in our book that takes the triangle C to triangle D in terms of an assignment of points. As you make some selections, other selections will be chosen for you. I would like you to try this exercise. Press pause on your video, and when you're ready for me to discuss it further, press play again. Here's my answer. I put the copy of the figure over on the answer so it'd be easier to explain. Triangle C is taken to triangle D, so C is mapped to D by a motion that appears to stretch C to D in the following manner. R prime is assigned to R, so here's R prime, it's assigned to R. S prime is assigned to S, T prime is assigned to T in such a way that the distance between O and R prime appears to be 2 times the distance between O and R. So as I look at this appears to be 2 times the distance from O to R. And the same appears to be true here. The distance between O and S prime appears to be double the distance as between O and S. The distance between O and T prime appears to be 2 times the distance between O and T, where U is any length. R is between O and R prime. Here's R, between O and R prime. S is between O and S prime, here and here. T is between O and T prime. And for any point V on C, and you can see I've drawn this this point there, the point V prime is assigned to it where the distance between O and V prime is 2 times the distance between O and V is between O and V prime. And we'll look at a mapping like this later on. This is actually referred to as a magnification, but again, we will study those more in depth as we progress through this unit. So this movement of the plane is a mapping. We can describe the motion of a figure from one position to another as the assignment by which to each point of the original figure exactly one point of the final figure is assigned. That is, such a motion can be described as a mapping or function from one set of points to another. Remember, a mapping is a situation where I have an input that has exactly one arrow out. So every point in that plane is assigned exactly one place. So although we are primarily studying mappings of the plane, many of these results also apply to mappings of space to itself. The first mapping that we're going to take a look at is called reflection. Reflections can be obtained by folding a piece of paper as shown below and then looking through the paper at the mirror image. So if I were to fold this paper, I could see the mirror image would look like this. That's reflection over a line. So here is a picture of a mapping of a reflection across a line. I have my line L drawn here. P reflects to T, T reflects to P, Q reflects to U, U reflects back to Q, and you get the idea. So the figure on the right, which R sub L is the reflection of pi across the line L in pi. This is the notation for a reflection over line L. So the way we write this is the reflection over line L of P is T. So P goes into the reflection, out comes T. The reflection over the line L of X is X. Notice X is on the line. I reflect it over the line. It goes right back to itself. I reflect U over my line, and it lands at Q. Now, some vocabulary. T is the image of P. X is the image of X. Q is the image of U. Whatever goes in, we refer to as the pre-image. And whatever comes out is referred to as the image. On this page, we're going to talk a little bit more about the notation and what is meant by R image. We're going to let R be a relation and let X and Y be such that X, Y, the ordered pair, is an element of that relation. Then Y is said to be an R image of X. Y is the R image of X because it's an element of that relation R. We're going to let A be a set. Then the R image of A is denoted R with this double quote mark of A. The double quote mark indicates that A is a set, not a point. Without the quote marks, it would just mean A is a point. So it's denoted R double prime of A. R image of A is the set of all R images of elements of A. Thus, for all Y, Y is an element of the R image of A if and only if there exists X in my set A, such that X, Y is an element of my relation. So again, this quote mark here means it's a set. So looking at our figure over here, T is the R sub L image of P. Notice, T is right here. It is the image of P. T is a point. P is a point. Okay, no quote marks there. If I let A be this entire set, all these points, and B be this set, and I were to reflect each of these points over L, so I'm reflecting a set, out would come B. So B is a set. This is a set. This is a set. So if I look at P, Q, R, K, S, and X, B is what comes out. T, U, V, K, W, and X. I reflect A over my line L, out comes a new set of points. So again, that double quote mark just refers to the fact that what is inside parentheses is a set, not a point. Okay, next I want you to work on exercise 119. Please pause your video, and when you're ready for the answer, press play and I will talk about it. Okay, here is the answer. We have a relation R. It is the +5 relation from real numbers to real numbers defined for all x and y. And x and y is an element of the +5 relation if and only if y is x plus 5. So if I want to put a into this relation, I simply take each of these numbers and I add 5 to them. So 3 plus 5 is 8, -2 plus 5 is 3, pi plus 5, square root of 3, square root of 3 plus 5. Now, I'm going to take this set and put it into that relation again. So simply add 5 to each of these again. This is what comes out. And in part C, I'm taking this set and I'm putting it into the relation again. Simply add 5 to each of these elements. That's the answer for C. So again, that's the +5 relation on real numbers. So now I'm going to release you to work on exercises 120 through 124 and also 126. Whatever you do not finish is homework.